Hello everyone. This is the final part of this week's lecture of Lecture 2, which are the fundamental mathematical tools. If you haven't read anything about the book from the book now, is the moment for you to pick up section 2.5 and read it. That is the most important section, and uh, you're going to see that the concepts are very simple, but I'm sure that as you haven't seen them before, they might take a while to sink down or to sink in. So I do recommend you to read this session in detail. We start by defining the neighbors of a pixel. There are various ways of defining various definitions. So let's see, assume that we have a pixel P at location XY, and it has neighbors. Basically, this notation is saying the following. So it has neighbors at x plus 1, at x minus 1, at y plus 1, and y minus 1. What it's saying is that you have a pixel here. If it has a neighbor here and a neighbor here, meaning that it's a pixel with a value, let's pick up a binary image that has only zero and ones, right? So the neighbors of a pixel in a 4 neighborhood are the horizontal neighbors, x minus 1 and x plus 1, and the vertical neighbors, y plus 1 and y minus 1. This is the definition of horizontal and vertical neighborhood, or 4 neighborhood. We can have a diagonal neighborhood, which is given a pixel here. A diagonal neighbor will be x plus 1, y plus 1 would be this guy here. X minus 1, y minus 1 would be this one here. X minus 1 and y plus 1, x minus 1 and y plus 1 would be this guy here. But basically the diagonals of a pixel. So as I said, this is a definition of a 4 neighborhood. If we get A and B, that's the definition of an 8 neighborhood, which is called an 8. So an 8 neighborhood of a pixel P here, any pixel, will be the pixel right above, right below, to the left, to the right, with all of its diagonals. This is an 8 neighborhood of a pixel. Given the definition of neighborhood, or pixel neighborhood, we can define the agency of a pixel. This will be related to the value V as the set of intensity values used to define agency. For agency is that where pixels P and Q that have the same value V are for adjacent. If Q is a 4 neighborhood, is a 4 neighbor of P. We're going to see examples of this in a minute. 8 agency is defined as pixels P and Q, again with the same values V, intensity values V. They are going to be 8 adjacent if Q is an 8 neighbor of P. So far, so good. The normal definitions of 4 neighborhood, 8 neighborhood are extended to agency. But now the M agency is a little bit different. So we say that pixels P and Q with the same values are M adjacent if Q is in the 4 neighborhood, and or Q is in the diagonal, and the set contain the 4 neighborhoods of P and Q, the intersection of this set has no pixels with the same value. Let's see examples of that. This is a distribution of pixels on a 3 by 3 matrix. Pixels in the picture B, which is this one. Let me pick up another pointer. This one. This is 8 adjacent to that, and that's 8 adjacent to that. That's 8 adjacent to that. The 8 adjacency would only see, well, there is a pixel. Let's see, we're talking about the adjacency of this pixel, the middle, the pixel at the middle. Is there a pixel with the same value on the top nearest vertical pixel? Yes, so that's adjacent. Is there one with the same value down? No, so there's no adjacency here. Is there a pixel on the diagonal? Yes, so that's adjacent, and that's adjacent, and that's adjacent. That's 8 adjacency. You see that you created a loop here. Maybe in some applications you don't want to have loops on adjacencies, because otherwise you may end up doing the same calculations with the same pixel over and over again. There are a few methods where you actually walk through the adjacency of pixels. So in these cases, it's better to use the concept of M adjacency, which is in this case, so you see that this is a diagonal. So the M adjacency says that if it's a diagonal, let's check if there is no intersection between the 4 neighborhoods. So this guy is a diagonal of that. So it's a candidate for M adjacency. So let's say it's 4 neighborhoods if there is an intersection. There is no intersection because there is no number, there's no pixel with the same value of this and that in the 4 neighborhood of this guy that intersects the 4 neighborhood of this guy. This is M adjacent because well, it's in the vertical top. This is M adjacent to this one because it's on the 4 adjacency of this one. What about these two? Are these two M adjacent? Well, this guy is on the diagonal of this one, so it might be a candidate, but the second condition is not respected, right? In this case, there is an intersection between the 4 adjacency of this number and the 4 adjacency of this number, which is exactly this number here. Therefore, there is no connection for an M adjacency. We can extend that to, we're talking about adjacency of pixels, which is a very simple measure. We can also have the same concept applied to regions. So consider that this is a region of an image, and this is another image, another region of the image. So we want to see, if I ask you whether this region Ri is a neighbor of, is 4 adjacent to the region Rj, you'd say no, because there is no connection with 4 adjacency here, but it is indeed M adjacent, because there is a pixel here, there is in a diagonal to the other pixel on the region, and there is no intersection between the 4 adjacencies of this pixel to that pixel. Okay. Just a second. Ready? Okay. Let's go. Let's move on. And with that, we can define the concept of digital path, which is basically following connected pixels. And the connected pixels, the pixels are connected if they are adjacent. That's the definition of digital path. So you pick up every pixel that's adjacent to another in a continuous way. A set of connected pixels in a subset of pixels S in an image is called a connected component of S. I'm sorry, I know that this may be a little bit abstract for now, and I urge you to go back to these concepts this week, still reading the related section on the book, but we're gonna use these concepts, so you have to know that. Otherwise, we are all gonna get a bit lost when we discuss the algorithms. Uh, as we discussed in the last section of this lecture, an image is nothing more and nothing less than a matrix. Therefore, we're going to manipulate images by using matrix operations. And there are plenty of them. So that's another point that I want to stress here. Be very careful about what kind of operation are you applying on the matrix. Usually, when we are doing matrix multiplication, we are not doing the normal matrix product that we are all well acquainted of. We're doing element-wise product, which is also called dot product or inner product. So whenever, it's not always, but in most cases, when you see a matrix multiplication, you're not doing line multiplied by the column summing that, right? You're doing this guy multiplied by this guy multiplied by this one, this one. The elements at the same with the same index are multiplied together, creating a matrix of the same size of the original matrix. Of course, there is matrix product. I don't need to explain what a matrix product is. You all know since, I don't know, the 5th grade, 7th grade or something. And there is the outer product. So there are 3 products that we use on image processing. Element-wise is the most common, matrix product, and the outer product. And the outer product, usually when you see the outer product, they use this symbol here. What they do is that if I want to multiply this vector with that vector, I get the first element of this vector multiplied by all of the other elements, all of the other coordinates of the other vector, creating one line of the result. And do the same thing for every single other element, creating new lines. So that's an outer product. Another concept that you're going to read over and over again in this area, it's very simple to understand, is the concept of linear and nonlinear operations. So consider an operator, any operator h, such that this operator is applied to a function f of some number with some pixel as argument, generating another function. Modifying the value of the pixel at this location, putting some other value, it's g, x, and y. Now, given 2 arbitrary constants a and b, and 2 arbitrary images, f1 of x and y and f2 of x and y, we say that the operator h is linear. Operator h is a linear operator if the operator applied to a linear combination of the functions f1 and f2. This is a linear combination because basically I'm just operating multiplying a constant to the function, then summing one function to the other and multiplying another constant to the other function. So applying this operator to this expression is the same thing as applying the expression to the operators. It's as if I could just get the operator and apply it to the functions. It's as if the operator could move inside of the linear this linear equation here, right? I'm moving the operator inside. So again, get rid of this. So h applied to a times f1 plus b times f2 will be equal, if this is equal to a times h applied to f1 plus b times h applied to f2. If it has the same value in both cases, h is said to be a linear operator. And we have a whole bunch of arithmetic operations, such as I can, they are all usually element-wise operations. If you read one thing like that, fxy plus gxy, what you're doing, you are summing two images, element by element, pixel by pixel, or subtracting, or multiplying, or dividing, and these are just arithmetic operations. There's a few very simple algorithms that we're going to play with on the first lab, hopefully, that applies noise reduction by using just elementary arithmetic operations. One of them is the image averaging. So what you do, given that you have a bunch of images of the same structure, let's say a galaxy somewhere in the space. So these are I have k images. Let's suppose that we have k images of a galaxy. The averaging, noise reduction by averaging, is just that I sum all of these images and divide by the number of images. It's the average. It's the average. Nothing more and nothing less than just summing up all of the images that you have and dividing by the number of images. What we get from that, that's exactly, that's in the book, that's figure 2.29 in the book. So this is an image of a galaxy pair. These are actual images, right? Actual photographs. There's a galaxy pair NGC 3314 that's corrupted by a Gaussian noise. You don't need to understand now what a Gaussian noise is. We're going to have a whole lecture about noise in the near future, right? And the next pictures are the results of averaging 5. This is the result of averaging with 5 images of the same galaxy with 10 images. So you see that this noise is kind of blurred and bad definition here is disappearing, and you're having an image that's much sharper than the initial one. This is the average of 20 with 20 images. This is the average with 50 images, and this is the average with this is wrong here. There should be 100 images averaged. So we have a very nice kind of sharp image of the galaxy with the averaging just by doing the average, just by doing sum and subtraction and division. Okay, so we can also use subtraction to compare images. This is an angiograph. The book has more details about how they obtain this angiograph. So you actually inject a substance in the vein, and then you take an X-ray of that. And the A is a mask image, B is a live image, and basically if I want to identify elements on this angiograph, what I do is I subtract, right? Just subtract this one. Let's say C is the difference between A and B. So subtracting this one from that one, I get this stuff here. And D is an enhancement. This image is an enhancement of that image. But you see that this is a kind of blurred image. This is a kind of, there are too many things here. I just subtract one from another. Subtraction, what we show is exactly the difference from one image to another. And then I use some algorithms for image enhancement and get a very nice detailed picture of it. We can use multiplication and division for shade correction. Let's say that we have one of these very Irritating effects. This is an electronic defect on a camera where one portion of the image is darker than the other. If I find a way of estimating this shading pattern, what I can do is that I can invert the shading pattern. By inverting it, I just mean taking the negative. I just subtract every pixel in this image by 1, and then in this case here will be white and this will be black. And I do a product of this with that, getting basically what we're doing with the product is the product with the reciprocal of this image is that I'm cancelling this effect. I'm cancelling this effect. Okay, getting a much better image on the other side. And this is the final bit. That's I think it's all of what I said is essential, but if I want to pick up one thing to actually learn today, is spatial operations. Spatial operations are those that are performed directly on the pixel of the image. They are of various forms: single pixel operations, neighborhood operations, geometric spatial operations. And neighborhood operations, what I do, we're going to see loads of these, but just to have you a general idea, we now know everything about the neighborhood of a pixel, right? So what I do, I use this neighborhood in some sort of calculation, and then apply the results of this calculation to the pixel itself. For instance, we're talking about averaging. In this case, we averaged the whole pixel, the whole image. I summed up the whole image 20 times and then divided by the number of images. I could do the same, but on a neighborhood. So I can average the values of the neighborhood, or basically I sum all of the intensity values of every pixel in this neighborhood in the matrix, and apply the average obtained to this pixel. The result is a blurring effect. So this is the original image, and this is the image where I apply this neighborhood averaging. Why do I want to blur the image? We're going to see loads of applications to that, especially on noise reduction and some very advanced algorithms for image segmentation. Bear with me for more 12 weeks, and we are going to see that in details. Geometric transformations are, well, the simplest ones are the affine transformations, also known as rubber sheet transformations, which are scaling, translation, rotating, and shearing. They are very easy. We're going to do that on the first or second lab, where we just get your original image, which a matrix, and multiply a transformation matrix. That's it. That's just a matrix multiplication. That in Python is one line of code. I wouldn't even call it code. I would call it a script. So there's a number of transformations of this kind, a number of matrices A that I can apply to an image. They are all very important. They are all used in a number of algorithms. So this is the identity matrix. This is scaling and reflection by a factor of Cx. This is the rotation. So if you get the original image is T here, applying the identity, I get T again. From the original T, applying a scaling, I get either a larger T or a smaller T, a T in a different scale. Applying rotation, obviously I have a rotated T. Translation, I have a T that is moved to, well, that's translated. It's a little bit self-explanatory. Shear is that kind of transformation where you pull the object from one side. So imagine these are all understood as rubber sheet transformation. So imagine that T is a rubber, it's just pulling and pushing from one side to the other and making this kind of rubber sheet transformation. That's shear vertical, and there is also shear horizontal, where you pull the objects by your horizontal sides. And finally, image registration. the idea is to align two or more images of the same scene. So imagine that I have a picture of my hand here and another picture of the same hand, but it's slightly dislocated. So what I want is to get these two images aligned. Oh, I can't make it with this camera, but you can have the idea. So I want to align one hand with the other by applying what? What am I going to be applying? This kind of geometric transformations. So in a nutshell, you transform the input image geometrically to produce an output image that is aligned or registered with a reference image. The transformation is usually not known, but must be estimated. Yeah, well, if you knew the transformation from the difference from one image to the other, you just apply the complement. The whole job of image registration is actually on the estimation process. One solution, typical solution used in the industry, largely used in various applications, is the use of tie points, or also called control points. The control points, let me show you an example before we go back to understanding this. These are these tiny white marks here. So this is the, I'm not sure if you can see that. If you can't, please have a look at the at this image on the book. That's on page around 95 or something. Well, you find that that's on section 2.6. So you see these tiny dots here. Imagine that there's in this example, this is the original image. This is the twisted, geometrically distorted image, and I don't have this one. I want to get the original image by from that. So what registration does, it identifies these points because it knows the location where these points should have been in the original image, and then with these points they form as a system of equations, and the solution of the system of equations are the transformations that you have to apply to get from this to this. Notice that this is not the original image. This is the image obtained from that by solving a system of differential a system of equations to find the transformations that I should do, the matrices that I should multiply on this image to get to that. Why do I know that? Because the book says it, it tells it, and also because if you get this image and subtract from the original image, I have this. So this is the difference. This is actually, these are artifacts that were introduced on the resulting image from the registration operation. And there's a whole bunch of other image transformations that we're going to see throughout in the next lectures. Basically, image processing and computer vision are all related to getting an image from a spatial domain, doing some sort of transformation, then you apply some operations, and you inverse to get to the normal domain. If you've done signal processing, you know that, right? You know that's a Fourier transform. So you get this image here. You apply a Fourier transform on this image. You get to the frequency space where you see these two dots here. Oh, wow. Imagine cleaning this image with this. It has this sinusoidal kind of interference here, typical of someone that turned on a hair dryer in the room next door on space, right? On the moon, and you have to fix that. Basically, you get the Fourier transform. You have these two very sharp, bright lights here, bright dots. You create a mask. Then you apply the transformation, this mask, to this image here, and you go back to the spatial domain, and you have, as a resulting, an image that's clear from this kind of sinusoidal noise. That's it, folks, and enjoy it. Please read, if you have one thing to read this week, read this section about mathematical, basic mathematical tools used in digital image processing. That's section 2.6. And I'll see you next time for chapter 3, where we start applying proper filtering algorithms. Thank you. Bye.